Okay, so we've defined displacement. From displacement, we defined velocity, and now we're going to use velocity to define acceleration. So the first thing we're going to talk about is average acceleration, and then we'll move on to talk about instantaneous acceleration, right? Just as we did for velocity. Right? The most important thing to have in your brain when you think about acceleration is this first sentence, right? Our conceptual understanding of acceleration is that acceleration describes the rate of change of velocity with time. Okay, so if we have velocity that is changing either in magnitude or direction, that means we have acceleration. Acceleration is a vector, just like velocity, and our definition of acceleration, in this case, the x component of our acceleration, our average acceleration, is given by this equation. Right? So again, we're going to do a, that's going to be our symbol for acceleration, a lowercase a, with a subscript x to denote this is the x component of our acceleration vector, and we can do the bar above that to represent an average, or we can do the little av here as a subscript to denote the average acceleration. And our definition of average acceleration is going to be our change in velocity in some given amount of time, right? Or a change in velocity is our final velocity, v2, my velocity at time 2, minus v1, my velocity at time 1. Okay, divide that divided by our elapsed time, right? t2 minus t1 is just how much time has gone on during the time in which this velocity change happened. Right? So as I said, velocity is a vector. That means that any change in its magnitude or its direction means you have acceleration. Okay. In terms of units, the units of acceleration are meters per second squared. Right? In our numerator, we have meters per second. In our denominator, we have seconds. So that gives us meters per second, or meters per second squared. Right? But then conceptually, thinking about this as meters per second may be a little bit more helpful, right? Because acceleration is a change in velocity. Okay, in terms of just picturing acceleration or average acceleration from a velocity versus time graph, right? So we've talked a lot about position versus time graphs, but we can also make velocity versus time graphs. So I can plot with this red curve my velocity as a function of time. It seems to be increasing with time. And I can pick 2 points on that line, right? At time 1, I can look at what my current velocity is, and that is given by v1. At time 2, I can look at what my current velocity is, and that's given by v2. And if I want to know the average acceleration during this time period from t1 to t2, I just draw a line between these 2 points, and I find the slope of this line. Right? The change in the velocity divided by the change in time is our definition of acceleration. That's also our definition of slope. Right? So the slope of that line is our average acceleration. Okay, just like we did for velocity, it's important to have some pictures in our head of what different accelerations are. So in everyday life, if you're on a train or something like that, you may experience something like 0.25 meters per second squared of acceleration. An elevator will actually accelerate even more, 2 meters per second squared. A really fast animal like a cheetah can accelerate at 5 meters per second squared. As we'll talk about later on this chapter, an object in free fall without any air resistance near the surface of the Earth will accelerate at 9.8 meters per second squared. So that's something relatively familiar. You can drop something and that's the acceleration you observe. Something like a space shuttle or an F-16 can give accelerations even greater than that, 29 for a space shuttle, 79 for an F-16, and things can get much larger for something like a baseball struck by a bat. That can be a huge acceleration, and absolutely huge accelerations happen at places like particle accelerators. So okay, talking about acceleration a little bit more. Acceleration is a vector, so we need to know how to figure out the direction of our acceleration. Is our acceleration positive or negative? And we have an equation for acceleration, so that should always be able to tell us, do we have positive acceleration or negative acceleration? But let's go through this a little bit using this image from the book. So at time 0, we have some velocity v sub 0 moving to the east, and we're at this location here. At some later time, our final velocity is now to the west, and we've also moved to the left a little bit here, so now we're left of the origin. Right, so what direction is our acceleration? Well, we had constant acceleration throughout this process. To the left, negative acceleration. Okay, how did that work? Initially, I have velocity to the right. I have positive velocity. If I have acceleration, constant acceleration to the left, If I'm moving to the right, that's going to cause me to slow down and slow down and slow down. Right? My change in velocity is going to be to the left. I'm slowing down, slowing down, slowing down. I'm going to come to a stop momentarily, and then I'm going to start moving to the left and speeding up to the left and speeding up to the left and speeding up to the left. Right? So that's how constant acceleration motion can actually make you change directions. And so here's our formula for average acceleration, change in velocity with time, or just plugging in with v naught for our initial velocity and v final for our final velocity. We can come to this equation, and this is just a vector equation, right? So we know how to add and subtract vectors. So v final is a vector to the left, v initial with a vector to a right. If I want to subtract v final minus v initial, I need to do v final plus minus v initial. Right, so I flip around my initial velocity, and now I can add together these two vectors with the tail to head method, and I get delta v. Right? Delta v is pointing to the left in the negative direction, and by our equation for acceleration, right, delta t is always positive, so it's always going to be delta v that determines whether acceleration is positive or negative. Right, so we can see here that we have negative acceleration and we have negative change in our velocity. Okay, so conceptually, acceleration is a change in velocity over some period of time, and the direction of our acceleration is determined by the change in the velocity. So let's do a few examples of this, because acceleration direction can be a little counterintuitive, whether it's positive or negative, and it's a really common source of mistakes, so let's go through a few examples. Okay, example 1, we have at time 0, or time 1, I'll call it, 0 seconds, we have some velocity to the right in the positive direction of 8 meters per second. Some later time, time 2, we're now moving to the right still, but only at 4 meters per second, right? So we've slowed down. So is this positive or negative acceleration? Well, we need to do v2 minus v1. So in vector form, we can do that, v2 minus v1. And if we do that vector math, we get a vector to the left. Right, so that kind of denotes that delta v is negative. Or we can do this with our formula. We can plug in our velocities. Our final velocity is 4. Our initial velocity is 8, so 4 minus 8. The amount of time that has elapsed is 2 seconds. So we get negative 4 divided by 2, or negative 2 meters per second squared. So we can see here that we have both a negative delta v and a negative acceleration. So this is negative acceleration. All right, so the point here is that if we have positive, we're moving in the positive direction and we're slowing down, that means we have negative acceleration. Right? We have positive velocity at all times, but that positive velocity is getting less positive. Right? So that corresponds to negative acceleration. And again, it's delta v that determines if acceleration is negative or positive. So delta v is negative, that means acceleration must be negative. Okay. So let's go to example number 2. Example number 2, at time 1, we're moving at negative 3 meters per second, right? So we're moving to the left relatively slowly. At time 2, we're still moving to the left, but now we've sped up, right? We're moving to the left at negative 9 meters per second, right? So is this positive or negative acceleration? Well, with a vector equation, we can do final velocity minus initial velocity, and so that's still going to be pointing to the left. So that shows us we have a negative change in our velocity, which means we have negative acceleration. Okay. Another way of saying this is with our equation. You plug in our numbers. Once again, negative 9 minus minus 3 is negative 6. So our delta v, our change in our velocity, is negative 6 meters per second. And so divide that by our time, and we find our acceleration of negative 3 meters per second squared. Right. So this is also negative acceleration, even though we are speeding up here, right? So it turns out in example 1, we were moving to the right, we were in the plus x direction and slowing down, and that was negative acceleration. But this time we're moving to the left in the negative x direction and we're speeding up, and that's also negative acceleration, right? So this can be counterintuitive, but we have to go with our physics definition of acceleration. And our acceleration definition tells us that if we're speeding up in the negative x direction, that is negative acceleration, right? We have negative velocity getting more negative, that corresponds to negative acceleration. Okay, so the kind of take-home message here is negative acceleration does not mean you are slowing down. And a second kind of take-home message is don't memorize this, always just think about delta v. If you can figure out what delta v is, you can figure out if acceleration is positive or negative, right? Final velocity minus initial velocity. If I'm moving faster or slower, and in what direction at the final time. Okay. Example 3 now, we're moving to the right and speeding up, and that is positive acceleration, as you may expect, right? And once again, delta v is positive, or our vector equation tells us that our delta v is positive. So if we're moving to the right in the plus x direction is speeding up, that's positive acceleration. But also if we're moving to the left and slowing down, that turns out to also be positive acceleration, right? So in this case, we do, with our acceleration equation, final velocity is -4, initial velocity is -8, -4 minus -8 is +4 meters per second, right? So our delta v is positive, that means our acceleration is positive, right? So if we have negative velocity, which is getting less negative, that corresponds to positive acceleration, right? So if we're moving in the minus x direction and slowing down, that's positive acceleration because the change in our velocity is in the positive direction, right? So again, the take-home message here is positive acceleration does not mean you are speeding up, right? It can also mean you are slowing down depending on which direction you're traveling. So again, don't memorize this. You can always figure this out using our equation for acceleration, which includes delta v in it. Okay. So let's get a little bit of a picture of how acceleration works from this nice video from Flipping Physics on YouTube. So I'll bring that up here and play this. So we just have a ball on a ramp, right, on an incline, a basketball, and it's just going to start that basketball rolling. And it's going to roll with constant acceleration down that hill because the force of gravity is a constant, and that our yellow vector there is a constant. But we can see what happens to the velocity vector. The velocity vector gets bigger and bigger and bigger, right? Because acceleration is a change in our velocity, and it's a positive acceleration here. So we're speeding up and speeding up and speeding up. Okay. You can actually look at the numbers. The acceleration is a constant, 2 meters per second squared, but the velocity is increasing and increasing and increasing, right? Every second, the velocity is getting faster by 2 meters per second. Right? And we can look at the plot here and see that again, the acceleration was constant, so the velocity was getting bigger and bigger and bigger, and the amount of distance traveled in each time interval is getting bigger and bigger and bigger because the velocity is increasing. We can also throw the ball up the hill with some initial velocity. We can see that now we have negative velocity but positive acceleration, so we're slowing down on the way up the hill and we come to a stop. Right? So we still have the same positive acceleration here, we just have negative velocity, so we're slowing down, slowing down, slowing down. So that acceleration, positive acceleration is causing our velocity to go from -10 to -8 to -6 to -4 to -2 to 0. Right? So our velocity is getting closer to 0, even though we have positive acceleration here, and the amount of distance traveled in any time interval is decreasing because our velocity is decreasing. And here we can throw the ball up the hill, and as soon as it starts rolling down the hill, we can also see how that compares to a ball rolling down the hill, and it looks exactly the same. Okay. So both of these correspond to the same positive acceleration. One is causing you to speed up, one is causing you to slow down. So I think that's a really nice video made by this guy, Flipping Physics, who has a lot of good videos on YouTube. So okay, back to our slides here. So we've talked about average acceleration. Now let's talk about instantaneous acceleration. Just like as we did before, instantaneous acceleration we're going to define by taking the limit that our time interval is going to go to 0 of our average acceleration, excuse me. And by definition, if delta t is going to 0, this is our definition of a derivative, right? So our instantaneous acceleration is going to be given by the derivative of our velocity with respect to time. All right, so if we know an equation for our velocity with respect to time, we can take the derivative of that and find an equation for the acceleration as a function of time. Or if we have a plot of velocity versus time, we can take a derivative or find the slope of a tangent line and find the acceleration. All right, so what's happening here is we can, as we did before, figure out the average velocity over some large time interval, right, by drawing these two dots and finding the slope of that line. And we can start to make that time interval smaller and smaller and smaller, right? If I make it this time interval, I have this slope to my line. If I make it this time interval, I have this slope to my line. I can make this time interval shorter and shorter and shorter, and eventually I get two dots that are pretty much on top of each other, and at the slope of that line is the slope of this tangent line here. All right, so that's what our derivative is. If I want to know the acceleration at exactly this point, I have to draw in a tangent line and find the slope of that tangent line. Okay, and so that's our our picture we want to have of what is instantaneous acceleration. At any point in this chart, I could pick a point, draw a tangent line, and the slope of that tangent line is my acceleration at that point. I should also note that we know that velocity is defined by the derivative of position with respect to time, so that means that acceleration is also the second derivative of position as a function of time. Okay, so to understand acceleration more, we will continue to use these nice simulations from the PhET collaboration. So you can click on this link and it'll bring you to this simulation, which should just open up in your browser, and you can move this person around on this number line and make position versus time graphs and velocity versus time graphs and acceleration versus time graphs, and that can really help you to understand this motion. So I really encourage you to do that. But let's take a closer look at a motion that I just made using this simulation. Here's a motion that I made. So this person starts off at the origin at x equals 0. They start moving in the plus x direction. Right? They walk all the way out to 5 and then all the way out to 10. They almost hit the wall. Then they turn around at this point and start walking backwards. So now they're going from 10 to 9 to 8 to 7, etc. At some point they get back to where they started, to the origin, and they start walking back in the negative direction, right? Getting more and more negative here until we get to almost -5 or so. And then this person stops momentarily and turns around and starts walking back. At this point we get back to the origin, and then we start again walking in the positive x direction, and then finally he hits a wall, right? Walks right into the wall. So we can understand our position graph. Now we can understand our velocity graph. The slope of the tangent line at any point in this graph is our velocity, right? So in this region we have 0 slope, we have 0 velocity. In this region I have some positive slope, I have some positive velocity. In this region I have even more positive slope, right? So I have a larger velocity. In this region I have negative slope, so I have negative velocity, etc. Okay. At this exact point I have 0 slope, so at that exact point I have 0 velocity, right? This is where we were turning around. Okay, so I think we've talked about that before. Now we want to understand our acceleration as a function of time. So I'm going to label this for us. Oops, let me show this one first. If I would go from velocity to acceleration, we can also see some relationship, right? On this part of my velocity versus time graph, I have 0 velocity. I also have 0 slope. Right, so if I have 0 slope here, that means I have 0 acceleration. My velocity is not changing. Right? In this region, my velocity is changing. Right? My velocity is changing with time, and it's changing. I have positive slope. I'm going faster and faster with time. I'm moving in the plus x direction, and I'm moving faster. That corresponds to positive acceleration. Right? I have positive slope, positive acceleration. You can see this velocity at this point starts increasing faster. Right, there's kind of a kink right here. It starts increasing faster. So the slope in this little section is even more positive, so that corresponds to an even larger acceleration. Okay. Then this person then starts having negative slope here, negative velocity, I'm sorry, not negative velocity, negative slope, which means we have negative acceleration. Right, so this corresponds to this person walking in one direction, coming to a stop, and turning around. Right, so throughout that motion, we had negative acceleration, causing us to slow down in our velocity, come to a stop, and start walking in the other direction, and speed up and speed up and speed up in the other direction. That whole motion was caused by this negative acceleration. During this region, we have positive slope, corresponding to positive acceleration. During this region, we still have positive slope, but it's less positive, so the acceleration is a smaller number, but still positive. Here we have 0 slope. Right, we're still moving, we still have positive velocity, but we have 0 slope, so we're moving, but our speed is not changing. So in that region we have 0 acceleration, but we're still moving quickly towards the wall, and all of a sudden we hit the wall, and our velocity suddenly goes to 0, and you can see here we suddenly have a very negative acceleration. Right, that's what causes us to stop. We're hitting that wall. So I hope this picture of thinking about this person moving around can help you in understanding acceleration, and I really encourage you to go use the simulation and try to understand the motion. Given a position versus time graph, try to predict the velocity. Given a velocity versus time graph, try to predict the acceleration. And you can also try to backtrack and try to think about, if you know this acceleration, can I figure out my velocity, etc. Okay. And I'll note one more thing is that acceleration is also related to the second derivative of position versus time, and you may remember that second derivatives are related to something being concave up or concave down. Right? So in this region where we have positive acceleration, we have concave up position versus time graph. In this region where we have negative acceleration, we have concave down position versus time graph. In this region where we have positive acceleration, we have concave up. So that's another interesting thing to note. And I won't go through this in detail. I just want to include one more link to this nice hyperphysics website, which has a lot of great resources. And they've got these nice position versus time graphs that are nicely lined up for us. And everything's nicely labeled, so you can try to, just another resource to help understand this motion. So thank you.